Let me ask you, what do you do when you're on an outdoor trip and your phone's battery is starting to get dangerously low, but you need to make an emergency call? Most people would answer, well, I grab my power bank and simply charge up my phone with it. Such little power banks are not only easily available and quite cheap to get, but can, due to their built-in lithium-ion battery, hold a decent amount of energy that can charge up my phone up to 65%. But let's say you already drained your power bank beforehand, because you had to power more important USB devices. How can we deliver our phone the required emergency charge? For that, I created this hand crank generator, which, after attaching its crank and connecting it to my modified power bank, can charge up the battery with up to 300 mA at a decent crank speed. After a couple of minutes of cranking, that charge is certainly enough for an emergency call. So in this video, let me show you what struggles I initially went through to create this gadget, so that at the end you can make your own much simpler version than what I planned at the beginning. Let's get started. This video is sponsored by JLC PCB, who currently upgrade their factory in order to offer 5 pieces of common 2-layer PCBs in a production time of only 24 hours without any additional fees. So upload your Gerber files to order high quality PCBs. Now, I initially planned to utilize this 900 kV BLDC motor as the hand crank generator. I got this idea from a viewer who asked underneath a video in which I demonstrated how to rewind a BLDC motor, whether I could use this technique to create a hand crank power bank. So I roughly spent around 10 hours of experimenting to find out that no, you cannot use a small BLDC motor as a hand crank generator. If that is enough explanation for you, then skip to the now presented time mark to see the functional generator solution, or stay around to experience my hopeless attempts to get the BLDC motor working. For first tests, I reassembled the motor that I took apart in the rewinding video and measured out the mechanical dimensions of the top side of the rotor. With those information, my assistant designed a rather slick looking crank, which after 3D printing it, fit perfectly onto the rotor and held its grip firmly while rotating. After then connecting the motor wires to my oscilloscope, we can see that the motor outputs a maximum of around 200 mV while rotating, which is way too low for the power bank circuit that takes a 5V input voltage, or the utilized lithium-ion battery that requires up to 4.2 volts for charging. So I disassembled the motor once again and removed the old motor phase wires from the stator, whose winding specifications were 3 0.2mm wires in parallel with 14 turns per stator pole. Next, I started thinking. In theory, we should get 10 times the voltage with 10 times the turns. To try that out, I used 0.1mm enamel copper wire and for starters did 100 turns per stator pole. After completing one phase with that technique, I temporarily reassembled the motor to see how much voltage it would output this time. And as expected, the voltage was a bit higher, with peaks of around 1 volt, which was a step in the right direction. But the big problem was that this one phase already featured a resistance of around 27 ohms. That means that, for example, in a star connection, one current path would feature a resistance of 54 ohms. If you would want to charge your battery with 4.2 volts and 100 milliamps, you would have a voltage drop of staggering high 5.4 volts, which means your generator needs to create a total of 9.6 volts. For that high of a voltage though, we would need way more windings, but because the space inside the small stator is limited, we would have to use even thinner wire, which once again increases the resistance, which on the other hand means we need a higher voltage. This is an unsolvable vicious circle. But since I'm quite stubborn, I got myself 2 new BLDC motors, this time with initially lower kV ratings of 460 and 268. And even with those, I was never able to output sufficient voltage and current at a low RPM. So all in all, small BLDC motors cannot be used. But thankfully I got a decent motor selection at hand. My recommended picks were those 3, all DC motors to which a gearbox is attached, whose job is to decrease the original high RPM of the motor to a lower RPM. To test them, I measured the dimensions of their shafts, created a crude prototype crank in 123D design, 3D printed them and pushed them in place. Afterwards, I connected the outputs of the motors to my oscilloscope to see how much voltage they output. The first one with 400 RPM outputs 4 volts, the 200 RPM one 5 volts and the 100 RPM one 10 volts. But of course that is not a sufficient criterion for exclusion. For that I removed the electronics from my power bank in order to find out where I could inject my generator voltage for charging. First off though, I added a 1N4002 diode and a 470 microfarad 35 volt capacitor to the motor outputs like it's shown here. The diode prevents the motor from creating a reverse voltage when cranked the wrong way around, and the capacitor smooths out the generator voltage. Now my first idea was adding a buck boost converter to the generator outputs to create a stable 5V output and connecting that to the inputs of the power bank circuit, which not coincidentally requires more or less stable 5V. But after practically building up the circuits and doing some testing, I realized that the output voltage of the buck boost converter was not really stable, which led to the quick destruction of the power bank circuit. So my final solution is much simpler, by directly connecting the smoothed out outputs of the generator to the battery. This way the generator acts like a constant current source, and thus slowly increases the voltage of the battery, which is no problem for the power bank circuit since it is used to such voltage levels. You only have to be careful when the battery is completely full, because this way you can easily overcharge it with the generator, which can lead to its destruction. And after doing a couple of tests with the circuit setup and the different generators, I found out that the 200 RPM one offers the most comfortable but sturdy torque and charges up the battery with up to 300 mA. Since the battery features a capacity of 2000 mAh, you would have to crank around 7 hours for a complete charge. Not very practical when you think about it, but for an emergency situation definitely usable. So next my assistant created a housing for the motor in 123D design, in which, after 3D printing it, I secured the motor with small screws. Afterwards I used 2-component adhesive to secure an XT60 female connector in the housing's lid, and once that was dry, connected it to the generator electronics, and finally closed the housing up with a couple of M3 screws. After I was then done assembling the crank, we created a modified backplate for the power bank. Once its 3D printing process was complete, I removed all of its support material, pushed 2 wires in its connector cavity and soldered those to another XT60 female connector, which I then secured in place with 2-component adhesive as well. As soon as the glue was dry, I directly connected the XT60 wires to the battery terminals of the power bank and closed it all up. After then creating a suitable male XT60 connector wire and adding silicone covers to the female XT60s, this project was finally complete, and ultimately might not have been my original vision for it, but still functions well. I hope you enjoyed this video. If so, don't forget to like, share and subscribe. Stay creative, and I will see you next time.